visual community detection, and evaluation of 2D, 3D perspective, and 3D stereoscopic displays. Nicolas Greffard, Fabien Picarougne, and Pascale Kuntz. Code Research Team, LINA, Polytech'Nantes, Rue Christian Pauc BP 50609 France 44306 Nantes Cedex 3. Nicolas, Greffard, Fabien, Picarougne, Pascale, Kuntz at University-Nantes FR at Universal-Nantes FR. Abstract. 3D drawing problems of the 90s were essentially restricted on representations in 3D perspective. However, recent technologies offer 3D stereoscopic representations of high quality, which allow the introduction of binocular disparities, which is one of the main depth perception cues, not provided by the 3D perspective. This paper explores the relevance of stereoscopy for the visual identification of communities, which is a task of great importance in the analysis of social networks. A user study conducted on 35 participants with graphs of various complexity shows that stereoscopy outperforms 3D perspective in the vast majority of the cases. When comparing stereoscopy with 2D layouts, the response time is significantly lower for 2D, but the quality of the results closely depend on the graph complexity. For a large number of clusters and a high probability of cluster overlapping, stereoscopy outperforms 2D, whereas for simple structures, 2D layouts are more efficient. Introduction. Long after the pioneering work of Kolmogorov, 3D drawings knew a phase of great interest in the mid-90s in the graph drawing community. Besides the beauty of the theoretical questions, this interest was mostly motivated both by the availability of new 3D display hardware and by the exploration of new applications which emerged in particular in VLSI design, e.g. 2. The most studied models included orthogonal grid drawings, convex and straight-line drawings, e.g. 3, 4, 5. And the most common aesthetic criteria were the bounding area volume, the minimization of edge length and bends. NP-completeness proofs were deduced from 2D for the different criteria, and several theoretical bounds were highlighted in different cases. And different algorithms and tools, e.g. Giotto 3D, GM, 3D, 3D Cube, were developed. 1, 2, 3, 4, 5. However, despite all these efforts, the 3D phase repeatedly declined, and it is sometimes considered as a prejudicial epiphenomenon in the graph drawing community. See Idza's invited talk at GD 101. The main criticism concerns the lack of layout legibility, often illustrated by the paradigmatic 3D drawing of K7. Someone. http://www.graphdrawing.org/GD2010/invited HTML. M. Van Creveld and B. Speckman, eds. GD 2011, LNCS 7034, pages 215 to 225, 2012, C225, Springer Verlag, Berlin, Heidelberg, 2012. 216. N. Greffard, F. Picarougne, and P. Kuntz. Encouraging results for the multilayer layouts have nevertheless continued to punctually draw the attention. But as said by Eads, they use 3D with a 2D attitude. The third dimension is added for representing a parameter, e.g. time. Nevertheless, we believe that the 3D trial is essentially due to a non-proper definition of 3D and consequently to an inappropriate choice of the aesthetics. In the works previously quoted, 3D drawings are 2D representations of a perspective view, and the aesthetics are directly reused from 2D without specific analysis of their adequation in 3D. Recent cheap technologies offer 3D stereoscopic representations of high quality, which allow the introduction of binocular disparities, which is one of the main depth perception cues, not provided by the 3D perspective. Stereoscopy may also be combined with virtual reality, e.g. 6, but this approach is far beyond the scope of this paper. Although the general question of the benef it's offered by stereoscopy over 2D still remains open, investigations on the 3D expressiveness are attracting a growing community of computer scientists, e.g. for an overview, 7.67. In graph drawing, recent works have shown the interest of stereoscopic 3D representations of node-link layouts of graphs for local analysis. In particular, 8 have experimentally confirmed the power of 3D, previously highlighted by 9, to trace out short paths between close, distance 2 or 3 vertices in limited-size graphs, with less than 150 nodes, 0.89. In this paper, we explore the relevance of stereoscopy for a higher-level task, the identification of communities, i.e. vertex subsets strongly connected to each other. This task is of great importance in the analysis of social networks where visualization knows an increasing interest. Most often, communities are first identified with a clustering approach for which various algorithms have been proposed. See 10 for a recent state-of-the-art, and visual representations of clustered graphs are then used. But the community detection suffers from a major problem. In many real-life situations, communities do not form a non-ambiguous partition of the graph, and several overlappings are present. In order to tackle this difficulty, alternative strategies have been developed, e.g. give a particular place to some predefined vertices, central actors, which are members of different communities, 11, or duplicate vertices which belong to different communities, e.g. 12. Other representations than node-link diagrams have also been proposed, but we here restrict ourselves to the latter, which is by far the most popular visual representation of social networks, and the only one to have been investigated in 3D.101112. Here, we do not propose an N+1th strategy, but we analyze the resort to stereoscopy for detecting communities in a crude representation of the whole graph, obtained with the Fruchterman-Reingold algorithm. Roughly speaking, the question we are asking in our experiments is how different is stereoscopic representation from 2D and 3D perspective views for identifying communities in medium-sized graphs with different complexities? Beyond its popularity, the choice of the algorithm, which has been shown to be outperformed in 2D by other approaches, is here justified by two reasons. It directly computes a layout. Visual community detection 217, which highlights communities without pre- or post-processings, and it is directly applicable to both 2D, 3D perspective and stereoscopy, which consequently limits bias in the comparisons. For pseudo-random graphs associated with different parameters such as the cluster size and the density of intra- and intercluster links, we conducted a user study. We asked participants the number of communities they could detect, and we measured the time required to answer. The rest of this paper is organized as follows. Section 2 briefly recalls some psychovisual generalities on human 3D perception which guide our research. Section 3 details the experimental procedure for the comparisons. Finally, the results are analyzed in Section 4. Stereoscopic perception. We live in a 3D space, and a long period of evolution has endowed us with organs that allow us to perceive a three-dimensional space from visual information. A huge amount of research in cognitive sciences has been dedicated to the mechanisms implied in the perception of 3D environment, e.g., 13. In addition to those associated with the shape and object detection, the biological mechanisms, which govern the perception of a distance in the optical axis, the depth dash, play a crucial role. Depth perception is certainly a combination of several perceptive mechanisms, and various studies have been carried out in the last decades to try to measure the relative performance of different functions and visual cues used by the human brain to perceive depth, e.g., 14, 15, 16. Roughly speaking, it seems that partial occlusion, an object partially in front of another one, is one of the most important factors, whatever the distance between the person and the object. For limited distances, less than 40 m, binocular disparities associ. Aided with stereoscopic vision and perspective motions also have an important effect, whereas for larger distances not considered in this paper, other factors like aerial perspective come into play. 17, 18. 0.1314151611718. The comparison of the relative effects of stereoscopy and motion cues is still widely discussed. They seem to be equivalent or complementary in various tasks, e.g. 19, 20. More precisely, motion itself associated with a 3D perspective may give a faithful depth reproduction. Object rotations jointly act with the spatial memory to form a 3D mental representation of the observed object. 15. But motion is also useful both in perspective and in stereoscopy to detect objects hidden in a particular vision axis. Consequently, measuring the interdependence between these two cues is a very difficult task. This paper restricts itself to the comparison of stereoscopy and 3D perspective, both combined with basic motion possibilities at a macroscopic level. However, the analysis of the specific effects of motion are in our short-term plans. 192015. Experimental design. 3 viewing methods were employed during the experiment. 218. N. Greffard, F. Picarougne and Key, Kuntz 2D. A 2D graph layout was computed with the Fruchterman-Reingold algorithm and displayed on a 2D surface. The users were allowed to zoom in/out on the graph using the mouse wheel and to apply a z-axis rotation on the layout by moving the mouse point. 3D perspective. 3D persp. A 3D graph layout was computed with the Fruchterman-Reingold algorithm and displayed on a 2D surface with a perspective projection. Along with the zoom in/out and the z-axis rotation, the user was allowed to spin the viewpoint around the graph. X/y-axis rotation. 3D stereoscopy. 3D stereo, the same 3D layout with perspective projection. As case 2 was used, but with 2 viewpoints computed in real time, to introduce the binocular disparity, 1 viewpoint for each eye, with a slight shift on the horizontal viewing axis to mimic the actual separation between the human eyes. The same interactions than in case 2 were allowed. 3.1 Apparatus. The visualization system ran on an Intel Core 2 Duo 3.00 GHz E8400 processor with 4 GB of RAM and an NVIDIA Quadro FX 3800 GPU. All graphs were displayed in shades of white on a black background using Gouraud shading, without projective shadows and an anti-aliasing algorithm to improve the quality of the display. The visualization was displayed on a white painted wall by an Acer H5360 3D projector, 30x1 30M2 screen, with a resolution of 1280 by 720 pixels. View angle of 0.05 degrees for a pixel in the center of the screen. Our system uses active stereoscopy with NVIDIA 3D vision shutter glasses. By using these glasses, we decrease the perceived luminosity. To avoid any bias and ensure the same level of luminosity for each viewing method, participants had to wear the glasses through all the experiment. Participants could also graph viewing space, detailed user interface, user workspace. Figure 1. Photograph of the experimental setup along with a snapshot of the user interface of the tablet PC. Visual community detection. 219. Interact with the system through a wireless mouse. The answers were entered using a touchscreen tablet PC. Different numbers were proposed, between 1 and 15, plus don't know, and participants just had to touch the corresponding number. The experimental setup can be seen on Figure 1. 3.2 Graph database. In order to analyze the stereoscopic viewing for different topologies, we have generated graphs with a classical pseudorandom model, e.g. 21. The generic model G21K NV pint text depends on 4 parameters: the number K of aprioricless, TERS, the number of vertex per cluster NV, the probability pint, resp pext ophege. Between two vertices belonging to the same cluster, resp different clusters. We have generated 480 graphs with parameters ranges specified as k is an element of 4, 5, 11, and v is an element of 10, 20, 30, 40, pext. Pint is an element of 0.02, 0.8, 0.02, 0.7, 0.03, 0.065, 0.6, 0.07, 0.6, 0.1, 0.8, 0.08, 0.6, 0.1, 0.8, 0.03, 0.7, 0.03, 0.6, 0.04, 0.7, 0.03, 0.5, 0.05, 0.8, 0.05, 0.7, 0.05, 0.6, 0.7. The parameters pint and pext were empirically mined during a previous study by 2 confirmed users. Furthermore, the largest graphs were discarded to avoid any performance issue. A few examples of such graphs are shown on Figure 2. 3.3 participants. 35 participants, 25 males, 10 females, carried out the experiment. Aged from 20 to 50, 30 of them were computer science students or researchers. 3 of the subjects were left-handed with a right-handed use of the mouse. Only 2 subjects had never visualized any stereoscopic material, and 11 out of the 35 participants were not familiar with 3D software such as video games. 3.4 Experimental procedure. To limit the experimentation duration, 15 layouts per viewing method were successively presented to each participant. To avoid any potential bias, the 3 viewing methods appeared in a random order, no interleaving. The 3x15 layouts were randomly picked from the database without duplication within the same viewing method. This process aims at avoiding any learning bias in the community detection task. The maximal task completion time was 28 minutes, 15 minutes on average. Before the experiment, a few questions were asked to the participants to gather their experience with graph theory, graph visualization, stereoscopic displays, and 3D software. A description sheet was handed out to briefly explain the experimental process, and a quick demo presented the 3 viewing methods with an easily readable graph, 3 clusters, 20 nodes per cluster, and a high pint and small pext. Then, the participants had to go through a training session to get familiar with the system. The training session consisted in 3 layouts of increasing complexity for each viewing method. Participants were asked to estimate the number of communities displayed as fast as possible and told that the experimenter couldn't help them. If a participant felt unable to detect communities, she was told to skip the layout. N. Greffard, F. Picarougne, and P. Kuntz. Figure 2. Snapshots of the drawings of graphs of increasing complexity. G1 equals G, K equals 4, NV equals 20, pext equals 0.05. Pint equals 0.8, G2 equals G, K equals 6, NV equals 30, pext equals 0.05. Pint equals 0.7, G3 equals G, K equals 8, NV equals 30, pext equals 0.07. Pint equals 0.8. Visual community detection. 221. By pressing a button labeled I don't know, once all the layouts of a viewing method had been presented, the following method started with a notice of the experimenter. You have finished the XDH series. We move on to the next series. At the end of the experiment, the participants were asked to state their visualization preferences, easiest and hardest cases, and their estimation, cases with the best and the worst performance. For results, 4.1 Quality of community detection. Let X be the set of answers given by all participants and I a subset of such that all the instances I of I share the same ratio range pec/pint. Let IANS be the number of communities proposed by a participant for an instance I. And 2 act the a priori number of communities in the model, section 3.2. For each viewing method VM equals 2D, 3D persp, 3D stereo, the error is measured by the average of the differences. Error I equals 1. Card I is an element of I. 2. ANS minus 2 act. Note that the answer I don't know was counted as an error, i.e. the detection of only one community, and that for high values of PEX and low values of pint the term error is not perfect since the detection may be very ambiguous. But in these cases, the quality measurement of the community detection remains an open difficult question. See Fortunato, 2010. The results depend on the complexity of the graph structuration here measured by the ratio PEX/pint. For small values, the communities are easy to identify, whereas for high values important overlappings and small community densities may make detection difficult. Table 1 shows that 2D is significantly better for a small complexity, 2-way ANOVA. P equals 0.01 communities are well separated on the layout and are easily detected on a plane. For larger complexities, stereoscopy is slightly better, 2-way ANOVA. P equals 0.1, in particular for large K. Table 1. Error for community detection. For each viewing method VM and for each interval of structure complexity, PEX/pint, I, mean error I, along with the cardinality of each interval. Complexity cardinality 2D, 3D persp, 3D stereo. PEX/pint. 0.02, 0.04, 0.04, 0.06, 0.06, 0.11, 0.11, 0.15, 369, 406, 405, 260, 0.100.37, 1.62, 3.27, 3.47, 1.64, 3.22, 0.27, 1.40, 2.78, 3.71, 2.99, 222. N. Greffard, F. Picarougne, and P. Kuntz. Table 2. Error for community detection. For each viewing method VM and for I, mean error I, depending on K. Complexity viewing method K equals 4K equals 5K equals 6K equals 7K equals 8K equals 9K equals 10K equals 11. PEX/pint. 0.02, 0.04, 0.04, 0.06, 0.06, 0.11, 0.11, 0.15. 2D. 3D persp. 3D stereo. 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 0.0. 0.0. 0.0. 0.0. 0.1, 0.05, 0.06, 0.16, 0.13, 0.67. 0.00.13, 0.08, 0.25, 0.35, 0.37, 1.56. 0.0. 0.00.07, 0.16, 0.11, 0.42, 1.67. 0.00140.001.272.65, 3.356.94, 0.0, 0.0, 0.000.080.581.451.924.135.93, 0.00130.90.630.693.815.5, 0.0, 0.51352.243.956.157.9, 0.00130.321.071.634.446.127.61, 0.0, 0.000.211.61.93.425.6.88, 0.280.882.4.696.147.139, 10, 0.731.232.35815.446.8.758.75, 0.931.352.064.755.258.6.66. Table 3. Standard deviation of the error for community detection for each viewing method and for a threshold of structure complexity, PEX/pint. Complexity 2D, 3D persp, 3D stereo, PEX/pint. Less than 0.061.281.16. Greater than or equal to 0.063.633.69. 1.67. 3.38. Values. Table 2 shows that for K greater than 7 stereoscopy is significantly better than 2D for a complexity greater than 0.06, two-way ANOVA, P equals 0.02. The additional perceptive dimension combined with the motion seems to help to distinguish the aggregates even in presence of noise overlappings. The situation is different for 3D perspective, for which occlusions partly explain the debased results. Nevertheless, let us note that, whatever the viewing method, the error variation is important as soon as the complexity increases. Table 3. We have observed that this variation is similar for any value of K. Moreover, in our experimental sample group, it cannot be explained by the nonfamiliarity with the 3D software, but complementary experiments are required to reject this hypothesis. For point 2 response time. For each viewing method VM, the response time is the average time of response time EVM, I, off participants. Table 4 shows that the response time for 2D is significantly smaller than for 3D whatever the graph complexity, and the response times of 3D perspective and stereoscopy are very similar. However, as discussed in the conclusion, a more precise analysis of the participant behavior, mouse motion, seems to establish that the time exploitation is different in the two cases. Visual community detection. 223. Table 4. Response time for community detection. For each viewing method VM and for each interval of structure complexity, PEX/pint, mean time EVM, I in seconds. Complexity 2D, 3D persp, 3D stereo, PEX/pint. 0.02, 0.04, 7.3. 14.2, 0.04, 0.06, 11.1, 17.9, 0.06, 0.11, 12.4, 22.5, 0.11, 0.15, 13.1, 21.9. For point 3 participant perception, 12.3, 17.7, 24.7, 21.1, Table 5 underlines participant preferences for the stereoscopy and difficulties felt with both 2D and 3D perspective. We are aware that a bias could exist. The experimentation by itself shows our interest in 3D to the participants who may be unconsciously inclined to share the researchers' enthusiasm. Nevertheless, part of the subjectivity is corroborated by the experimentations among the participants who estimated that their best results were obtained with stereoscopy. 54% had their intuition confirmed by the results, whereas only 15.5% of them obtained their best results with the 3D perspective. Consequently, the reject of 3D perspective recalled in the introduction is verified. But the comparisons show that this subjective perception is significantly different from stereoscopy. Table 5. Subjective perception of the participants. For each viewing method VM, percentage of participants who answered that the case VM is the easiest, RESP the hardest, and the one for which they believe to obtain the best, RESP worst, performances. NA. Don't know. Answer. Easiest. Hardest. 2D, 3D, PERSP, 3D stereo NA. 14.2. 37.1. Best performances 11.3. 0. 43. 0. 68.6, 17.2. 5.7. 14.2. 74.3, 14.4. Worst performances 43. 5 conclusi. 34.3. 5.7. 17. As far as we know, this paper presents a pioneering research in the use of stereoscopy for a visualization problem which has known an increasing interest in the last decade, the detection of communities in large graphs. Our first experiments highlight an important difference between stereoscopy and classical 3D perspective, which has been widely criticized by the graph drawing community. Moreover, even if the debate remains widely open, experimental results seem to show the interest of stereoscopy against 2D for complex structures with numerous clusters of variable density and many overlappings. Obviously, additional. 224. N. Greffard, F. Picarougne, and P. Kuntz. Experiments are needed to confirm these results on larger populations and real-life databases, and to better understand the observed differences. In the near future, our objective is to go beyond the measurement of errors by apprehending more precisely the role played by motion in 3D environment. To that aim, during the experiments we stored the mouse movements for each participant. A first superficial analysis highlights important use differences between 3D perspective and stereoscopy. This research could lead to investigating new optimization criteria in the graph drawing community, which take into account not only the aesthetics of the layouts, but also the handling for their interpretation and use. 1. Kolmogorov, A. Barsden, Y. Abora realization of sets in three-dimensional space. Problems Cybernet, 1967. 2. Rosenberg, A.L. Three-dimensional VLSI, a case study. J. ACM 30, 397 to 416, 1983. 3. D. Batista, G. Patrignani, M. Bargiu, F. A split and push approach to 3D orthogonal drawing. In Whiteside's SH edition, GD 1998. LNCS, volume 1547, pages 87 to 101. Springer, Heidelberg, 1999. For Eads, P. Symbones, A. Whiteside's S. Three-dimensional orthogonal graph drawing algorithms. Discrete Applied Mathematics 103, 1-3, 55 to 87, 2005. Wood, Dr. Optimal three-dimensional orthogonal graph drawing in the general position model. There, Comput. Sci. 299, 151 to 178, 2003. 6. Halpin, H. Zielinski, D. Brady, R. Kelly, G. Exploring semantic social networks using virtual reality. In Chess, AP, Staub, S. Dean, M. Paolucci, M. Maynard, D. Finnan, T. Thurnarayan, K. eds. ISWC 2008. LNCS, Volume 5318, pages 599 to 614. Springer, Heidelberg, 2008. 7. Tysar, A. Campo, M. An Overview of 3D Software Visualization. IEEE Trans on Visualization and Computer Graphics 15, 1, 114 to 135, 2009, 8, where C. Mitchell, P. Visualizing Graphs in 3 Dimensions. ACM Transactions on Applied Perception 5, 2 to 15, 2008, 9, Belcher, D. Billinghurst, M. Hayes, S. Stiles, R. Using Augmented Reality for Visualizing Complex Graphs in 3 Dimensions. In ISMAR, pages 84 to 92, 2003. 10. Fortunato, S. Community Detection in Graphs. Physics Reports 486, 75 to 174. 2010, 11. Aubert, D. Chiricota, Y. Jordan, F. Melanchon, G. Multiscale Visualization of Small World Networks. In Infovi's 2003, Proceedings of the IEEE Symposium on Information Visualization, Infovi's 2003, pages 75 to 81, 2003, 12, Henry, N. Vazirianos, A. Fekete, J.D. Improving the Readability of Clustered Social Networks Using Node Duplications, 2008, 13, Landy, M. S. Maloney, L.T., Young, M.J., Psychophysical Estimation of the Human Depth Combination Rule. Volume 1383, pages 247 to 254. SBIE 1991, 14, Habona, G.S., Wheeler, P.N., Shira, G.W., Brandt, M. The Relative Contributions of Stereo, Lighting, and Background Scenes in Promoting 3D Depth Visualization. ACM Transcomput, Hum. Interact. 6, 214 to 242, 1999, 15, Van Schuten, B.W., Van Dyke, EMG, Zudalova Sainstra, E. Suanisia Putra, A. Reiber, J.C. The Effect of Stereoscopy and Motion Cues on 3D Interpretation Task Performance. In Proceedings of the International Conference on Advanced Visual Interfaces, AVI 2010, pages 167 to 170. ACM, New York, 2010. Visual Community Detection. 225. 16. Where C. Mitchell, P. Reevaluating Stereo and Motion Cues for Visualizing Graphs in 3 Dimensions. In Proceedings of the Second Symposium on Applied Perception in Graphics and Visualization, APGV 2005, Volume 95. ACM 2005, 17 Cutting, J. How the Eye Measures Reality and Virtual Reality. Behavior Research Methods, Instrumentation, and Computers 29, 29 to 36, 1997, 18, Saraceni, C. Franck, R. Bielyumel, E. Bellardinelli, M. Comparing Distance Perception in Different Virtual Environments. Cognitive Processing 10, 294 to 296, 2009, 19, where C. Frank, G. Evaluating Stereo and Motion Cues for Visualizing Information Nets in 3 Dimensions. ACM Transactions on Graphics 15, 121 to 139, 1996, 20, Domini, F. Kodak, C. Tassinari, H. Stereo and motion information are not independently processed by the visual system. Vision Res 46, 1707 to 1723, 2006, 21, Garbers, J. Promel, H.J. Steger, A. Finding Clusters in VLSI Circuits. In Proceedings of ICAD 1990, pages 520 to 523, 1990.